Hi. So, today we will be solving some problem from simple linear regression model. That is the first topic we talked about, and here is one problem from simple linear regression model. A study was made on the effect of temperature on the yield of a chemical process. The following data were collected in a coded form. So, this is the x stands for the temperature and y is the yield of a chemical process. So, y is the response variable and x is a regressor variable, and we want to fit a simple linear regression model here. So, we are given 11 observations here. Okay. So, the first question is, this is quite straightforward. The first question is assuming a model like y equal to beta naught plus beta 1 x plus epsilon, what are the least square estimates of the regression coefficient beta naught and beta 1, and what is the fitted equation. Okay. We have solved similar problems in the while we are talking about the simple linear regression model. And then the second question is construct the ANOVA table and test the hypothesis that beta 1 equal to 0 with level of significance 0.05, and then what are the confidence limit for beta 1, and the fourth question is what are the confidence limit for the true mean value of y when x equal to 3. Okay. Let me start with the first one. So, we are given these observations x I y I for I equal to 1 to 11, and first we will be fitting a simple linear regression model using the least square technique. Okay. So, what we are given is that we are given x I and y I for I equal to 1 to 11, and we want to fit a model like y equal to or y I equal to beta naught plus beta 1 x I plus epsilon I. Okay. So, we know that this beta naught and beta 1 they are obtained by minimizing the least square function, that is s, which is equal to y I minus beta naught hat minus beta 1 hat x I. So, this is the ith residual, and by minimizing this one for I equal to 1 to 11, we get the least square estimate of the regression coefficient beta naught and beta 1. So, beta 1 hat we know that this is equal to s x y. Please refer my first topic, simple linear regression. So, s x x. Okay. So, this can be also written as summation x I y I minus n x bar y bar. So, here n is equal to 11, and by sum over x I square minus n x bar square. Okay. So, you are given x I y I for I equal to 1 to n. So, what you do is that best thing is that you compute sum over x I summation y I summation x I square summation y I square and also the product x I y I, then you are done. Okay. So, you can compute all these things for the given observations, and then you can check that this one is equal to 158 by 110, which is equal to 1.44. Okay. And beta naught hat is equal to y bar minus beta 1 hat x bar, and you can check that this one is 102 by 11, that is 9.27. So, we are done with the first problem. So, the fitted equation is y I hat is equal to 9.27 plus 1.44 x I. So, this is the fitted model for the given problem. Okay. So, the next problem is it says that construct the ANOVA table and then test the hypothesis that H naught, that beta 1 equal to 0 at level of significance 0.05. Okay. So, now construct the ANOVA table. Okay. So, source of variation, degree of freedom, sum of square, MS MS and the F statistics. Okay. The source total variation, that is SST. So, SST is equal to summation y I minus y bar square, I is from 1 to 11, and you can check that this is equal to 248.18. Okay. So, the SS total is 248.18. Now, it has, what is the degree of freedom? Degree of freedom is 10, because you know that this y I minus y bar, they satisfy a constraint like summation y I minus y bar is equal to 0. So, there is one constraint here. So, that is why 1 degree of freedom less here. Now, you can compute SS regression. SS regression is beta 1 hat square S x x, and we know that beta 1 hat is 158 by 110 square, and S x x is 110, right. So, this is equal to 226.94. Well, so this is regression here, and the SS regression is 226.94, and the degree of freedom here. See, SS regression is also equal to E I square from I equal to 1 to 11. So, this is another way to compute. You have the fitted model, you know y I hat, you have the original observation y I. So, you can compute E I for I equal to 1 to 11, but you don't have the freedom of choosing all the E I's independently, because there are two constraints on E I. So, you can choose 9 residuals. I mean, you have the freedom of choosing 9 residuals, and remaining 2 have to be chosen in such a way that that those 2 restrictions are satisfied. Okay. So, the degree of freedom for SS regression is equal to 9, and then the remaining part, the part which remain unexplained, the part of variability, that is SS residual, okay, and that has degree of freedom 1, and the SS is obtained by SS total minus SS regression, that is 22.23. Okay. And the MS value is sorry, I said the residual degree of freedom is 9. Yeah. So, this is the residual degree of freedom, and the regression degree of freedom is equal to 1. Okay. So, the MS residual is SS residual by the degree of freedom, that is 2.36, and the MS regression is SS regression by degree of freedom, that is 226.94. So, the F statistics is MS regression by MS residual, which is equal to 96.17. Now, you know that we can test this hypothesis, say H naught, that is beta naught equal to 0 against H 1, that beta 1 is not equal to 0, using this F statistics, and the observed value of F is equal to 96.17, and this has degree of freedom 19. So, you compute you check the tabulated value of F 0.05 19. So, that is equal to 5.12. So, F is the observed F is greater than the tabulated F. So, what the conclusion is that we reject H naught, that is beta 1 is equal to 0 is rejected. That means, there is a linear relationship between y and x. Okay. So, the next problem is what are the confidence limit for beta 1. Okay. So, we have a point estimation for beta 1. Now, we will find the confidence limit for beta 1. Okay. So, before doing that, maybe you know already, but I want to say that another way to test this hypothesis, that H naught beta 1 equal to 0 against H 1 beta 1 not equal to 0. This can be tested also using the T statistic, that is T equal to beta 1 hat by MS residual by S x x. I hope you know all these things. So, this is the T statistic under the null hypothesis that beta 1 is equal to 0, and this follows t distribution with the degree of freedom n minus 2. So, here it is 9, and you can check that this t value is beta 1 hat is 1.44 and ms residual is 2.36 and s x x is 110, and you can check that this value is 9.83. Okay. And now, you look at the tabulated value of t, that is t 05 degree of freedom 9, that is equal to 1.833. So, again of course, you will get the same result whether you use F statistic for testing the hypothesis or you use the t statistic for testing the hypothesis, the result will be the same. And also in fact, F is equal to t square under the null hypothesis. Okay. So, here again the observed value is greater than the tabulated value. So, we reject H naught, that beta 1 is equal to 0. Okay. So, next we will go for the third problem. What are the confidence limit for beta 1 at 0.05 level of significance? Okay. So, for this one the question is, what are the confidence limits at alpha equal to 0.05 for beta 1. Okay. So, what we know is that we know that this beta 1 hat which is a linear combination of y i's, and y i's follow normal distribution. So, linear combination of normal distribution is again normal. So, this follows normal distribution with parameter with mean beta 1 and variance sigma square s x x. Okay. So, I can write this one as again beta 1 hat minus beta 1 by sigma square by s x x. This follows normal 0 1. Okay. But what happens is that this sigma square, the population variance is usually unknown. So, we need to estimate this one. We estimate this one by ms residual, and once you replace this sigma square by ms residual, this follows t distribution. So, beta 1 hat minus beta 1 by ms residual s x x, this follows t distribution with degree of freedom n minus 2. And from here I can say that beta 1 hat minus beta 1 by ms residual s x x, this less than equal to t alpha by 2 n minus 2 and greater than t alpha by 2 n minus 2 degree of freedom, of course, minus this has probability 1 minus alpha, that is 0.95, and from here we get the 95% confidence limit for beta 1. So, this can be written as so the beta 1 from here, beta 1 less than equal to beta 1 hat plus T alpha by 2 n minus 2 and of course, multiplied by this thing m s residual by S x x, and here beta 1 hat minus T alpha by 2 degree of freedom n minus 2 m s residual by S x x. Again this has probability 1 minus alpha. Okay. So, that this is the lower limit for beta 1 and this is the upper limit for beta 1. Now, we know everything, we know what is beta 1 hat, we can find this tabulated value. This is T 0.025 because alpha is 0.05 and we know all these values. Okay. So, you can check that. Finally, this beta 1 is so let me put beta 1 hat here. So, this is 1.44 and the T value is 2.263 and the standard error of beta 1 hat is 0.146. Okay. And similarly, here 1.44 minus 2.263 into 0.146 and here is the limit for beta 1, it is 1.77 and 1.11. Okay. So, till now these problems we have already discussed in the module, I think even 4 also. It says that the fourth problem is that what are the confidence limit for the true mean value of y when x is equal to 3. Okay. So, what does this mean? We have to find the confidence limit for the true mean value, that is mean of y or expected value of the response variable at x equal to 3. And in the first module or module in simple linear regression model, we denoted this one by expectation of y given x equal to 3. I mean maybe we should not use this notation because x is not a random variable, right. So, but both are same, this is what I want to say here. Okay. So, we have to find the confidence interval for this mean value at x equal to 3. Well, so how to do that? So, what we want is that we want a confidence limit for E y at x equal to 3. Okay. Well, so let me write this thing instead of x 3, I will write that we are looking for say 95% confidence interval for mean value of y at say x equal to x naught. So, x naught is nothing but 3, that I will plug at the end. Okay. Let me solve this in general for x naught. So, this is nothing but beta naught plus beta 1 x naught, right, because we considered the model y equal to beta naught plus beta 1 x plus epsilon. So, the expected value of y at x naught is this one, because expectation of epsilon is equal to 0. And first what we will do is we will find an unbiased estimator for this one. an unbiased estimator of this one, this at x equal to x naught. That means, the unbiased estimator of beta naught plus beta 1 x naught is nothing but beta naught hat plus beta 1 hat x naught, because beta naught hat is an unbiased estimator of beta naught and beta 1 hat is an unbiased estimator of beta 1. Okay. So, well, so this one, so the unbiased estimator beta naught hat plus beta 1 hat x naught, this is a point estimator for the expected mean at x equal to x naught, and we are looking for a confidence interval for this one. So, this follows normal distribution with mean beta naught plus beta 1 x naught, and you can check that this has variance sigma square 1 by n plus x naught minus x bar whole square by s x x. Okay. So, of course, then this minus the mean by square root of this follows normal 0 1, and if you replace this sigma square by ms residual, then that follows t distribution. So, let me write that only. So, what I can do now, that beta naught hat plus beta 1 hat x naught minus the mean beta naught plus beta 1 x naught, and we are looking for a confidence interval for this one. This by ms residual 1 by n plus x naught minus x bar whole square s x x square root. This follows t distribution with the degree of freedom n minus 2, right. And from here, now yeah, of course, you know it. So, the whole thing, let me call it say A. So, A less than equal to t alpha by 2 n minus 2 minus t alpha by 2 n minus 2, this has probability 1 minus alpha, right, where A is nothing but this variable. Okay. So, from here we will get a confidence interval for beta naught plus beta 1 x naught, which is the mean response at x at the point x equal to x naught. Okay. So, what we will get from there is that beta naught plus beta 1 x naught is less than beta naught plus beta 1 hat x naught plus t alpha by 2 n minus 2, and then the standard error of this one, that is ms residual 1 by n plus x naught minus x bar whole square s x x. And similarly, here the same thing, beta naught hat plus beta 1 hat x naught minus this one, that is t alpha by 2 n minus 2. They are quite straightforward things. Okay. ms residual 1 by n plus x naught minus x bar whole square by s x x. So, this will go here. Well, so you are done. So, you have to know everything here, whatever you need, and finally, you can check that, or should I put them? So, we know that this one is let me do for the upper limit, that is 9.27, this part, and then this is n equal to 11. So, it is 9 degree of freedom and alpha is 0.05. So, alpha by 2 is 0.025. So, that is 2.262, and then you have here the ms residual is 2.36 and n is 11 plus x naught is 3, okay, and x bar is 0 here. So, 3 by 3 square by s x x, that is 110, right. So, this one is the upper bound for beta naught plus beta 1 x naught, and you can check that this one is 9.27 plus, okay, I think I said something wrong, 9.27 is beta naught only. So, plus beta 1 into x naught, that is beta 1 is 1.44 into x naught, that is 3. So, this whole thing is going to be equal to, you can check that this is nothing but 15.03 is the upper limit beta 1 x naught, and the lower limit you can check, that is 12.15. Okay. So, we found confidence limit for mean response at the point x equal to 3. Now, this might be little we did not try this one before. What it says is that what are the confidence limit at 0.05 level of significance for the difference between the true mean value of y when x 1 equal to 3. So, that is nothing but the mean value of y at x 1 equal to 3 and the mean value of y, that is E y at say x 2 equal to minus 2. So, this problem says what is the difference between these, not what are the confidence limit for this one. Okay. So, if I call this one say Z 1 and let me call this as Z 2, what are the confidence limit for Z 1 minus Z 2. Okay. Now, just now we know now what is the unbiased estimator for this one. So, the unbiased estimator for Z 1, for simplification, the unbiased estimator for Z 1 is nothing but beta naught hat plus beta 1 hat x naught, sorry, here it is x 1. So, 3, and the unbiased estimator for Z 2, call it Z 2 hat, that is equal to beta naught hat plus beta 1 hat minus 2 into minus 2. Okay. And thus the unbiased estimator for Z 1 minus Z 2 is Z 1 hat minus Z 2 hat, which is equal to beta naught hat plus beta 1 hat 3 minus beta naught hat plus beta 1 hat minus 2, which is nothing but beta 1 hat into 5, and we know that beta 1 hat is equal to 1.44 into 5, which is equal to 7.20. Well, so what we did is that we found a point estimation for Z 1 minus Z 2, and the point estimation is 7.21. Now, we have to find a confidence interval for Z 1 minus Z 2. So, what I have to do is that we have to find a distribution for Z 1 hat minus Z 2 hat, and for that we need to compute the variance of Z 1 hat minus Z 2 hat is nothing but variance of 5 beta 1 hat, right, because that is what we got here. So, Z 1 hat minus Z 2 hat is 5 beta 1 hat, right. So, this one is nothing but 25 into variance of beta 1 hat, right, and this is equal to 25 into sigma square by S x x, which is equal to 25 sigma square by 110. Okay. So, Z 1 hat minus Z 2 hat, which is an unbiased estimator for Z 1 minus Z 2, that follows normal distribution with mean Z 1 minus Z 2 and variance 25 sigma square by 1010. And then again this minus this by square root of this follows standard normal, and if you replace this sigma square by m s residual, then it is t distribution. So, Z 1 minus Z 2 minus Z 1 minus Z 2 by square root of 25 m s residual by 110. This follows t distribution with degree of freedom n minus 2, right. And from here I can write that Z 1 minus Z 2 is then less than equal to Z 1 minus Z 1 hat minus Z 2 hat plus T alpha by 2 9 degree of freedom, and here it is 25 into m s residual is 2.36 and S x x is 1 on naught. Okay. And similarly, here also it is Z 1 hat minus Z 2 hat minus T alpha by 2 9 degree of freedom by the same thing 25 into 2.36 by 1 naught. And finally, we know that this one is 7.2 naught, right. So, finally, it is the confidence interval for Z 1 minus Z 2 is 8.86 and the lower limit is 5.54. Okay. So, this is how we find the confidence interval for the mean difference at two different points. Okay. Well, so the first problem was quite easy, and this sort of problem we already solved in the first module or in the first topic. Now, we will go for the second problem, and here I recommend you do not look at the solution first, you try independently, and then if you can solve it independently, that means you have understood the things. Well, here is the problem. Consider the simple linear regression model y equal to beta naught plus beta 1 x plus epsilon, where the intercept is known. So, this is something new. So, for this linear model, the beta naught is already known. Okay. Then what you have to do is that find the least square estimator of the slope beta 1 for this model. This is the first problem. Then what is the variance of the slope beta 1 hat for the least square estimator found in part 1. Okay. So, you find a least square estimator of beta 1, say that is beta 1 hat, then find the variance of beta 1 hat. And the final problem is that it says that find the confidence interval for beta 1, and is this interval narrower than the estimator for the case where both slope and intercept are unknown. Okay. You try to solve independently, and then see my solution, and here is the solution. The first part is you are given a model y I, you have to fit this model beta naught plus beta 1 x I plus epsilon I, and epsilon I satisfy all this assumption, assume that normal 0 sigma square. The only thing is that here beta naught is known. Okay. So, only you have to find the least square estimator for beta 1 hat. Okay. So, how do we find that? We will compute the least square function s, which is equal to E I square. Okay. What is E I square? E I square is y I minus y I hat square, which is equal to y I minus y I hat is beta naught minus beta 1 hat x I. So, see here I did not put hat, because this is the parameter we do not need to estimate, we have to estimate only beta 1. And then this is the least square function, and then you find beta 1 hat in such a way that this is minimum. Okay. So, we have to differentiate this least square function with respect to beta 1. This is equal to 0 implies that summation y I minus beta naught minus beta 1 hat x I into x I is equal to 0, and from here I get that y I minus beta naught into x I equal to beta 1 hat summation x I square. Okay. So, this implies that my least square estimator for beta 1 is equal to summation y I minus beta naught x I by summation x I square. Okay. So, this is the, so we are done with the first part. This is the least square estimator for beta 1 hat when beta naught is known. The second problem is you find the variance of beta 1 hat. Okay. The second part is find the variance of beta 1 hat, and what is the beta 1 hat? Beta 1 hat we just found that this is equal to summation y I minus beta naught into x I by x I square, right. Okay. So, the variance of this one. So, here only random variable is y I, right. So, this one is equal to the variance of summation y I minus beta naught into x I, variance of this by summation x I square whole square. Okay. So, this one is equal to they are all independent, y i's are independent. So, this is x I square variance of y I, right. Variance of y I minus beta naught is nothing but variance of y I, because beta naught is a constant for I equal to 1 to n by summation x I square whole square. And variance of y I, we know that variance of y I is equal to sigma square, right. So, we can put now the sigma square into x I square by summation x I square whole square. So, this is equal to sigma square by summation x I square, yeah, right. So, this is the variance of beta 1 hat. Okay. And then the third problem was you find a confidence interval for beta 1 hat. Okay. So, the last part was find a confidence interval for beta 1. Okay. Well, so we know the variance of beta 1 hat. Let me check whether beta 1 hat is unbiased. So, you find the expectation of beta 1 hat. So, that is nothing but expectation of summation y I minus beta naught x I sum over x I square, and this one is equal to y I minus beta naught is nothing but beta 1 x I, right, from the model you get into x I. So, you put the expectation inside, right, by summation of x I square. Well, let me make it clear. So, you can put this expectation and bring this expectation inside. So, y I minus beta naught, y I is equal to beta naught plus beta 1 x I plus epsilon, right. So, expectation of y I minus beta naught is equal to expectation of beta 1 x I plus epsilon I, and expectation of epsilon is equal to 0. So, it is expectation of beta 1 x I, which is beta 1 x I. Okay. So, this one is beta 1 into summation x I square by summation x I square, that is nothing but beta 1. So, what we found is that expectation of beta 1 hat is equal to beta 1. So, the beta 1 hat is unbiased, right, and we also know the variance of beta 1. Okay. So, beta 1 hat follows normal distribution with mean beta 1 and variance sigma square by summation x I square, and then the usual technique, this minus this by square root of this follows standard normal, and then beta 1 hat minus beta 1 by, if you replace this sigma by m s residual by x I square, then what you get is that this follows T distribution with degree of freedom n minus 1 here. Okay. This is the residual degree of freedom, and you should understand that here the model is y naught y equal to beta naught plus beta 1 x I plus epsilon I. So, y I is this, and here while minimizing this least square function s, which is equal to E I square, there we differentiated this one with respect to beta 1 only. So, there is only one restriction on epsilon I, and so you have the freedom of choosing n minus 1 E I independently, and then the last one has to be chosen in such a way that that restriction is satisfied. So, that is why the S S residual here has degree of freedom n minus 1, not n minus 2. So, this is one point, right, and from here you can check that we can write that beta 1 hat minus beta 1 by m s residual by summation x I square, this less than equal to T alpha by 2 n minus 1 T alpha by 2 n minus 1 minus this has probability 1 minus alpha. Okay. And then finally, what we have is that we have the interval for beta 1, that is beta 1 hat plus m s residual summation x I square T alpha by 2 n minus 1, and the lower bound is beta 1 hat minus m s residual by summation x I square T alpha by 2 n minus 1. This is the lower bound for this. Now, what happened in the usual case when both beta naught and beta 1 are unknown, we get this confidence interval for beta 1. There we get it is beta 1 hat plus m s residual, by here you will get s x x into T alpha by 2, and the degree of freedom is n minus 2. So, this is the upper limit, and the lower limit is similarly beta 1 hat minus m s residual by s x x into T alpha by 2 n minus 2. Now, the question was is this interval narrower than the estimator for the case where both slope and intercept are unknown. So, this is the case when both intercept and beta 1 they are unknown, and this is the case when beta naught the intercept is known. Okay. Now, whether this interval is narrow than this one, how to check that? See, S x x is equal to summation x I square minus n x bar square. So, which implies that S x x is smaller than summation x I square. That means, this one is larger than this one is larger than this one. Okay. So, from here I can say that M s residual by summation x I square is less than equal to M s residual by S x x. So, this one is larger than this one, and again from the t table you can check that t value for this one t alpha by 2 n minus 2 is larger than, because here the lower degree of freedom is larger than t alpha by t alpha by 2 n minus 1. So, both this one is larger than this one is larger than this one, right. Okay, I should not write square root till that. So, that is why of course, that this interval is narrower than this one. The final answer is yes, this interval is narrower than the interval for the case where both beta naught and beta 1 and beta naught are unknown. Okay. So, now we have to stop. So, tomorrow again in the next class we will be talking about some more problems on regression. Thank you.